Special relativity theory, a critical review of attempts to justify the contradictory results. Part 1. Analysis of Dr. Don Lincoln's argument in Fermilab YouTube video, Relativity, How People Get the Time Dilation Wrong. How the content is arranged. For a better analysis, I have divided this video into 5 parts and shown their written content. In each section at the top of the screen is a brief description of the video content and my opinion on it. At the end you can find my final argument and conclusion. At the beginning, Dr. Lincoln points out the unusual consequences of the special relativity theory. He introduces the particular results of this theory, such as the shrinking of moving objects and the slower running of moving clocks, and makes the listener expect these issues to be clarified. He goes on with the time dilation equation, T sub 2 equals gamma times T sub 1, in which T sub 1 is the time shown on the clock by moving observer and experienced by him, and T sub 2 is the same time experienced by stationary observer. The Lorentz factor gamma is 1 over the square root of the quantity 1 minus v squared over c squared. Gamma equals or is greater than 1.
Einstein's theory of special relativity has fascinated the public for about 100 years. People hear about clocks running at different speeds, objects shrinking, and a myriad of peculiar other effects. And people might be willing to accept those sorts of assertions, but when they start thinking about relativity, they come up with what seems to be paradoxes. And then they begin to doubt the theory because, well, paradoxes. One such paradox is the oft-quoted statement that moving clocks tick more slowly than stationary ones. This is the whole basis of the ideas of interstellar travel, where a person heading at high speed on a spaceship to a distant star ages more slowly than a person stuck on Earth. If that rings a bell, that's the basis of the famous twin paradox of special relativity. I'll actually make a video focusing entirely on the twin paradox, but in this video, I want to really drive home some math that shows you have to be ultra, mega, extremely careful when you claim that there's a paradox in relativity. So let's start with the most common time dilation equation you'll find in a relativity textbook. It is T sub moving equals gamma times T sub stationary. T sub moving is the time experienced by someone who sees the clock moving. T sub stationary is someone who doesn't see the clock moving, and gamma is a factor unique to relativity. It's called the Lorentz factor. It is equal to 1 for something not moving and greater than 1 when something is moving. Gamma is simply 1 over the square root of the quantity 1 minus v squared over c squared. That'll be important in a little bit, but for the moment, just remember that gamma is greater than or equal to 1. At this point, it's probably helpful for you to watch 2 other videos of mine, specifically the one on the derivation of the gamma factor and the second one introducing Einstein's equations. I won't assume that you've seen them as I go through the rest of this video, but what I say here will be a little bit clearer if you've got those 2 under your belt. Okay, so let's get back to the time equation. What it says is simple. Given that gamma is greater than or equal to 1, it means that the time experienced by a person seeing the clock move is more than the time experienced by someone who doesn't see it move. And this means that someone moving ages more slowly than a person who isn't. Now this sounds crazy, but it's been proven to be true, and I made a video about that as well. It's called Einstein's clocks. So this idea is behind a lot of science fiction, and it's true to a degree.
Dr. Lincoln describes time dilation and illustrates the problem in detail. He speaks of 2 observers and their clocks with relative speed v to each other. He explains that according to the theory of relativity, each of these observers would see the other observer's clock running slower than his own. and says they can't both have clocks ticking faster than the other. That just makes no sense at all. Either we have logically proven that relativity is just bogus, or there's something more to it. Given that the scientific community still embraces relativity, there has to be something more to it. He continues, and the answer is both very subtle and technical.
But it's not the entire story. There are two key points I want to make here. The first is that this makes absolutely no sense. Not because the two clocks tick at different rates, although that's pretty weird, but because of an ambiguity. Suppose you label the two people as number 1 and number 2. If we take number 1 as seeing the clock to be stationary and number 2 as seeing it moving, we see that number 2 experiences more time than number 1. However, relativity requires that the laws are the same, no matter who is not moving, and this poses a problem. Suppose that we say number 2 is stationary with respect to his clock, and number 1 says that the clock is moving. Then number 1 experiences a longer time. Okay, so this is a problem. If you pick person 1 to be the stationary with a clock, then person 2's clock ticks faster. If you pick person 2 to be stationary with a clock, then person 1's clock ticks faster. And both people are equally right in saying that they're stationary. They can't both have clocks ticking faster than the other. That just makes no sense at all. Either we have logically proven that relativity is just bogus, or there's something more to it. Given that the scientific community still embraces relativity, there has to be something more to it. And the answer is both very subtle and technical. So let's dig into that.
He uses the Lorentz transform equations, showing the position and time with x sub 1 and t sub 1 in the moving frame, and with x sub 2 and t sub 2 in the stationary one. X sub 2 equals gamma times quantity x sub 1 plus v times t sub 1. T sub 2 equals gamma times quantity t sub 1 plus v over c squared times x sub 1. He says, let's pick two locations, say the location of observer 1 and observer 2 as seen by observer 1. By the first x sub 1 and t sub 1 are 0 and t sub 1, and by the second, x sub 1 and t sub 1 are minus v times t sub 1 and t sub 1.
So, begin by putting up the most basic and general equations of relativity. These are called the Lorentz transforms, and they show how you can translate between the point of view of two observers who are moving with respect to one another. Let's put up the time dilation equation I mentioned before as well. Notice that the Lorentz transforms have both a position and time equation. We're not interested in the position one here, so we'll get rid of it, and we'll change the symbols for the time one so it looks more like you usually see in the textbooks. So the first thing you see is that the time dilation equation is a special case of the more general one. They're the same only if that extra term of v over c squared times x substationary equals 0. And that is true only if either the velocity v is 0 or x stationary is 0. The first one is pretty trivial, as that means that the two people aren't moving with respect to one another, and so you don't need relativity theory at all. But the second is a lot trickier. It says that the time experienced by the person seeing the clock moving depends both on the time experienced by the person not seeing the clock move and by the location in the frame of the person who sees the clock to be stationary. So that's a big point. What it means is that we have to be very careful about defining which clock we're talking about. There are many clocks stationary with respect to each observer. Since they're at different locations, we need to take that into account. Since this is a core point of this video, I want to explicitly show what this means. Let's start out by just talking about one observer, which we'll call number 1, who is stationary with respect to the clock. We draw him here with his clock. But that's not the only clock in his world. He has clocks at every location, and since those clocks aren't moving with respect to him, all of those clocks are ticking identically. Now let's add in observer 2. He sees observer 1 moving to the right at velocity v, and he wants to know what he thinks the moving clocks will read. To do that, we will use the Lorentz transforms, but to do that, we need to figure out the locations. Let's pick two locations. Say the location of observer 1 and observer 2 as seen by observer 1. Observer 1 always thinks his location is x sub 1 equals 0. Since observer 1 thinks observer 2 is moving to the left at velocity v, he sees observer 2's position is changing. According to observer 1, observer 2's position is just x sub 1 equals minus v times t sub 1. Let's stop the motion and concentrate just on the two locations and times as seen by observer 1. His own location is simply x sub 1 t sub 1 equals 0 t sub 1. Now let's write down observer 2's location as seen by observer 1. It is just x sub 1 t sub 1 equals minus v times t sub 1 t sub 1. We can now use the Lorentz transforms for time. Let's first find out what observer 2 thinks the time is at observer 1's location. We just put in the value seen by observer 1. In doing so, we find that t sub 2 equals gamma t sub 1. That's just the normal time dilation equation.
For location, x sub 1 equals 0, by moving observer, t sub 2 equals gamma times t sub 1, and for location, x equals minus v times t sub 1, by stationary observer. T sub 2 equals t sub 1 over gamma. And that's all. What he gives as evidence to answer the questions about the controversial aspects of the theory. But this only means that the amount of time a not moving observer experiences depends not only on the time that the moving observer experiences, but also on the position of the clock. But this is not enough to answer the objections.
Now let's do the same thing for how observer 2 sees what observer 1 sees at observer 2's location. Remember that observer 1 sees this location as x sub 1 t sub 1 equals minus v t sub 1 t sub 1. We start with the equation t sub 2 equals gamma times the quantity t sub 1 plus v over c squared times x sub 1. We put in the x and t seen by observer 1. Thus, we get that t sub 2 equals gamma times the quantity t sub 1 minus v squared over c squared times t sub 1. So that's pretty easy. We can factor out the t sub 1 and get this equation here. And at this point, we can use the definition of gamma, which I remind you is 1 over the square root of the quantity 1 minus v squared over c squared. That means that this equation can be written as t sub 2 equals gamma divided by gamma squared times t sub 1. And finally, we get t sub 2 equals t sub 1 divided by gamma. That's divided, not multiplied by. That's exactly the opposite thing we saw when we looked at what was happening at observer 1's location.
Dr. Lincoln says, this means that the transformation for what observer 2 sees compared to what observer 1 sees depends on the location. But this is not the expected convincing subtle answer to the objections, as an example of two clocks moving with velocity v relative to each other, as he himself writes down, and both people are equally right in saying that they are stationary. They can't both have clocks ticking faster than the other. That just makes no sense at all.
Now we need to step back and review a bit. This means that the transformation for what observer 2 sees compared to what observer 1 sees depends on the location. Observer 2 sees more time elapsed than observer 1 sees at observer 1's location, but sees less time elapsed than observer 1 sees at observer 2's location. This is a super subtle point, but it clearly says that comparing clocks between two moving observers is a tricky business. You need to take into account both the time each experiences and the location at which the comparison is going on. Further, they both agree that the remote person's clock is slower. You probably need to think long and hard about this and maybe even rerun this video to get your head around this idea. A crucial point here is that when people start grabbing equations from relativity textbooks without understanding exactly what the equations mean, then they'll almost certainly make a mistake. And perhaps the most important point is that you ever, and I do mean ever, find something about relativity that sounds weird to you, always go back to the Lorentz transform equations. They will never let you down. Okay, so that might have been a mind bender, but I hope it taught you not to be cavalier about using relativity. And of course, I welcome your comments and hope you'll like the video and subscribe to the channel. Plus, share the video with your friends so we can help people understand that you need to be careful with relativity. In the meantime, remember, physics is everything.
Dr. Lincoln's approach in responding to the objections and contradictions related to the time dilation in Einstein's special relativity theory is to use the main equations of Lorentz transform instead of the simplified formula T sub 2 equals gamma times T sub 1 obtained for the position x sub 1 equals 0. And by calculating T sub 2 equals T sub 1 over gamma for the position at which the stationary observer is located, shows that time dilation does not always mean that the moving clock is slower. While acknowledging this, the contradictions he spoke about remains unresolved, and this method leads to new contradictory result, as discussed below. Given a constant value for T1, let's write the time equation T sub 2 equals gamma times quantity T sub 1 plus V over C squared times x sub 1 a bit different. T sub 2 equals gamma times V over C squared times x sub 1 plus gamma times T sub 1. T sub 2 is a line function of x sub 1 with a slope of gamma times V over C squared that intersects the T sub 2 minus axis at T sub 2 equals gamma times T sub 1, x sub 1 equals 0. The point of intersection of this line with the x sub 1 axis is T sub 2 equals 0, x sub 1 equals minus T sub 1 times C squared over V. And as seen before, T sub 2 equals T sub 1 over gamma, x sub 1 equals minus V times 1, and for another value of x sub 1, you can find even T sub 2 equals T sub 1. That is, the stationary observer will read different values for T sub 2 at any given time T sub 1 of the moving frame. On the top right in Minkowski diagram, one can find for a given T sub 2 different pairs of x sub 1 T sub 1. In other words, one on the Earth will see the clocks on a long moving spaceship running at different rates. But these clocks are stationary relative to one another and have to run at the same rate. Conclusion: if the time dilation were real, as Einstein explains, then T sub 2 equals gamma times T sub 1 plus gamma times V over C squared times x sub 1 would mean that every clock positioned in a distance x sub 1 from observer 1 ticks different from clocks in other different distances from him. But as Dr. Lincoln correctly says, let's start out by just talking about one observer, which we'll call number 1, who is stationary with respect to the clock. We draw him here with his clock. But that's not the only clock in his world. He has clocks at every location, and, since those clocks aren't moving with respect to him, all of those clocks are ticking identically. So another contradiction is added to the previous contradictions. Unless we consider the time dilation to be unrealistic and let not lower physics to the level of fiction. The discussion will be continued. Thanks for watching.